As we leave the scorched landscapes of Venus and the delicate, life-sustaining balance of Earth, our attention turns to a world that seems both familiar and alien: Mars. Known for its rust-red hue and its prominent role in both science and science fiction, Mars is the fourth planet from the Sun and the most Earth-like of all other worlds in our solar system. At infinity beyond, we see Mars not merely as a dusty desert, but as a time capsule, a planet that once may have looked remarkably like our own. Despite its current barren appearance, Mars offers countless clues that it was once a very different place. Satellite images and rover missions have revealed the unmistakable signs of ancient riverbeds, dried lake basins, and even delta formations. These features are not speculation. They are geological evidence of water's enduring presence on the surface of Mars billions of years ago. One of the first breakthroughs came from NASA's Viking orbiters in the late 1970s. They revealed vast channels that could only have been carved by flowing liquid. Later missions, particularly Mars Global Surveyor and Mars Reconnaissance Orbiter, added layers of high-resolution imagery, exposing complex networks of valleys and mineral compositions that form only in the presence of water. Then came the rovers. Spirit and Opportunity, twin explorers sent by NASA in 2004, drastically changed our understanding of Martian history. They found clear signs of past hydrothermal activity, water-altered rocks, and minerals like hematite and gypsum that could only form in wet conditions. Later, the Curiosity rover, still operating today, discovered evidence that Gale Crater once held a long-lasting freshwater lake. Organic molecules, the building blocks of life, were detected in the sediments. All of this data points to one astonishing conclusion: Mars was once warm and wet, with a climate potentially suitable for life. Around 3.5 to 4 billion years ago, the red planet may have had a thicker atmosphere, a stable water cycle, and even a magnetic field to shield it from solar radiation, conditions remarkably similar to early Earth. So, what happened? At Infinity Beyond, we explore the prevailing theory that Mars lost its magnetic field early in its history. Without this protection, the solar wind, a stream of charged particles from the Sun, began stripping away the planet's atmosphere. Over millions of years, the once thick air thinned to a whisper, and with it, the ability to retain heat and water vanished. Mars transitioned from a potentially habitable world to a frozen desert. Today, Mars's atmosphere is less than 1% the density of Earth's. Temperatures fluctuate wildly, from a high of 20 degrees C, 68 degrees, during the day, to lows of 100 degrees sun, 148 degrees at night. The water that remains is mostly locked in polar ice caps or exists as traces of vapor and salty brine in the soil. The planet is dry, cold, and hostile, but not lifeless in its past. The importance of Mars lies not just in its potential for ancient life, but in its accessibility. Unlike Venus, Mars has a surface we can explore with rovers, landers, and eventually humans. It has seasons, weather patterns, and polar ice. For all its challenges, it remains our best chance at exploring what a second genesis of life might look like, or what happens when planetary protection fails. As we study Mars with increasing precision, from orbit and on the ground, we are slowly unraveling the mystery of a world that may once have teemed with life. And at Infinity Beyond, we believe Mars holds the keys not only to understanding the past, but also to shaping the future of human exploration. While the surface of Mars appears cold, dry, and lifeless today, recent discoveries suggest that the red planet may still possess the ingredients necessary to support microbial life beneath its surface. At Infinity Beyond, this possibility sparks one of the most exciting scientific quests of our time, to determine whether life ever existed on Mars and whether it might still survive, hidden in the shadows of the Martian underground. One of the most compelling reasons to believe in this possibility lies in the evidence of subsurface water. In 2018, radar data from the European Space Agency's Mars Express orbiter revealed something remarkable beneath the southern polar ice cap, a 20-kilometer wide lake of liquid water buried under 1.5 kilometers of ice. This discovery, while still debated, opens the door to the existence of underground aquifers, environments shielded from the harsh surface where microbial life could potentially endure. Similar analogues exist here on Earth. Deep beneath Antarctica, in subglacial lakes such as Lake Vostok, microbes have been found thriving in complete darkness, under immense pressure, isolated from the surface for millions of years. If such extreme life forms can exist on Earth, why not on Mars? In addition to water, Mars presents seasonal plumes of methane, recorded by both orbiters and the Curiosity rover. Methane is unstable in the Martian atmosphere, breaking down rapidly under solar radiation. This means any methane observed must have been released recently. On Earth, over 90% of methane comes from biological processes. Could similar processes be occurring below the Martian crust? While methane can also be produced geologically, the cyclic and localized nature of its presence on Mars raises tantalizing questions. NASA's Perseverance rover, which landed in Jezero crater in 2021, was specifically designed to answer some of these questions. Jezero is an ancient river delta where water once flowed into a large lake. The delta's layered sedimentary deposits are ideal for preserving biosignatures, chemical or structural clues left behind by life. Equipped with instruments capable of detecting organic molecules, scanning rock cores, and caching samples for a future return to Earth, Perseverance represents our best chance yet to solve the Martian mystery. At Infinity Beyond, we follow every sample drilled, every spectrum analyzed, every grain of Martian soil examined. Because this mission is more than a robotic expedition, it is a direct search for ancient life on another world. And what's more thrilling is that we are planning to bring pieces of that world back home. The Mars Sample Return mission, currently in development through a collaboration between NASA and the European Space Agency, will attempt to retrieve the samples collected by Perseverance and return them to Earth by the early 2030s. Analyzing Martian soil and rock in Earth-based laboratories will provide levels of precision impossible to achieve remotely. If signs of microbial life, fossilized or preserved, are discovered, it would mark one of the most profound scientific achievements in human history. And even if no signs of life are found, the mission will still dramatically enhance our understanding of planetary formation, climate evolution, and the chemical pathways that lead to habitability. It will inform future crewed missions to Mars, providing crucial insights into soil chemistry, radiation exposure, and environmental hazards. The implications stretch far beyond Mars itself. If life once arose independently on the red planet, it suggests that life may be a common phenomenon in the universe, not a singular fluke confined to Earth. It would mean that given the right ingredients and time, the universe is likely teeming with biology, waiting to be discovered. At Infinity Beyond, we believe that in the dusty plains and ancient deltas of Mars, the past is whispering to us. We're listening, carefully, patiently, and with unshakable curiosity. As our robotic explorers continue to peel back the secrets of Mars, the next frontier looms large, sending humans to the red planet. At Infinity Beyond, we see this not just as an engineering challenge, but as one of the most ambitious dreams humanity has ever dared to pursue. A step toward becoming a truly multi-planetary species. The concept of a manned mission to Mars has existed for decades, living in the pages of science fiction novels and echoing in the ambitions of space visionaries like Wernher von Braun and Carl Sagan. But now, with rapid advances in technology, international collaboration, and private spaceflight, that vision is beginning to take shape in the real world. NASA's Artemis program aims to return humans to the moon as a stepping stone for deeper space missions. The experience gained in operating on the lunar surface, especially establishing sustainable life support systems, in situ resource utilization, and long-term human health monitoring, will provide critical knowledge for an eventual trip to Mars. Meanwhile, agencies like SpaceX are pushing the boundaries even further. Elon Musk's vision of using the Starship launch system to carry humans to Mars has ignited a renewed sense of urgency and possibility. Though the timeline is still uncertain, the groundwork is being laid. Launch systems are being tested, closed-loop habitats are being designed, simulated Mars bases have already been constructed on Earth, from deserts in Utah to volcanic slopes in Hawaii.